Welcome to this explainer. I am your strategist, and today we're diving deep into the theoretical architecture of Cambridge mathematics. We are tackling the absolute beast that is advanced integration. Specifically, we're going to master integrating linear compound functions, things like e to the power of ax plus b, 1 over ax plus b, sine of ax plus b, cosine of ax plus b, and sec squared of ax plus b. Now, to set the stage, I want you to picture a real Cambridge mathematics past paper question. We usually see two types of students tackle this. First, we have Alex. Alex overloads the page with raw mathematical facts, basically word vomiting every single integration rule they've ever memorized, but completely failing to analyze what the command word of the question is actually demanding. Then we have Sam. Sam rushes the process, frantically trying to beat the clock, missing the command word requirements entirely, and completely dropping crucial constants of integration. Both of these missteps, they result in slashed marks and lost opportunities. You know, whether you started your journey building foundations with IGCSE 0580 or O-Level 4024, or maybe you pushed into the add math territories of 0606 and 4037, you have been building up to this exact standard. Today, we're going to transform those common errors into precise, lethal execution. Think of mathematical rules as magic spells, structural frameworks where casting the right spell, applying the right method in the exact right context, guarantees maximum marks. Let's unlock the ultimate Cambridge exam strategy.
So you really have to wonder, why do so many students just hit an absolute brick wall when it comes to these specific linear compound functions? Well, stepping up to the 9709 A-level standard requires a massive mental shift. You are no longer just memorizing that the integral of cosine is sine. That won't cut it anymore. You're dealing with composite functions now. When you see something like sec squared of ax plus b, your brain has to simultaneously recognize the standard trigonometric integral while perfectly executing the reverse chain rule. It's an incredible cognitive load. The most common failures happen when candidates fall back on that rote memorization instead of adopting what I call the examiner's mindset. Just staring at the function, panicking, and hoping the numbers fall into place will not work here. Instead, we are building a rock-solid structural framework today that will bulletproof your methodology and protect you from these exact errors under that intense exam pressure.
Here is our masterclass syllabus for today. First, we'll uncover the ultimate integration trap. Then, we will break down the core theoretical foundations, moving right into the procedural framework. After that, we transition into problem solving and evaluation, and finally, we'll wrap up with insider examiner insights. Let's get right into it.
Section 1. The ultimate integration trap and what absolutely everyone gets wrong. Let's expose the trap that catches even the absolute best, most well-prepared candidates completely off guard: cognitive overload. Picture this. You're integrating 1 over ax plus b. You know it involves the natural logarithm, but in the heat of the exam, candidates just freeze. They forget the 1 over a coefficient, they drop the mandatory absolute value signs, or worse, they differentiate the inside function and multiply instead of divide. Look at the principal examiner reports. They highlight 3 massive, recurring pitfalls stemming from this exact overload. Number 1, confusing cause and effect. With a function like e to the power of ax plus b, students constantly differentiate the power and multiply by a instead of integrating and dividing by a. It's a classic mix-up. Number 2, forgetting format and presentation. Things like leaving out the dx in your notation, failing to use brackets appropriately, or just entirely forgetting the constant of integration. And number 3, providing answers not specific to the context. Listen, if a question explicitly asks for an exact volume of revolution and you give a rounded decimal answer instead of leaving it in terms of pi and exact fractions, the examiner is going to penalize you heavily.
The actual difference between a standard answer and a top-tier full-mark execution entirely comes down to your structural framework. A standard approach, like what our student Alex does, treats the integral as an isolated piece of knowledge. It just spits out the calculation with zero flow. A top-tier answer, however, explicitly references cross-topic connections and establishes principles through a highly logical, step-by-step mathematical framework. Think of it like applying the Peel framework: point, evidence, explanation, link, but adapted for mathematics. You state your point, which is the mathematical principle or formula being applied. You provide evidence by clearly substituting the given values and limits. You give your explanation by executing the integration using proper reverse chain rule mechanisms. And finally, you link the evaluated numerical answer back to the specific real-world context of the problem. That kind of clear, step-by-step mathematical reasoning is exactly what turns a bunch of red pen marks into green check marks. Now, before we continue and really tear into the core theoretical foundations, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2. Core Theoretical Foundations. Let's look at the actual architecture of integration.
The architecture of integration at this A-level standard requires you to kind of see the matrix of the mathematics. When you're evaluating the integral of sine of ax plus b, you shouldn't just see a basic trigonometry problem. You need to see a geometric transformation, a bounded area, a rate of change that is actively being reversed. Cambridge actively targets specific cognitive domains to test this depth. Knowledge and understanding? That's just your baseline. That's just knowing that integrating cosine gives sine. Application is taking that rule and using it on cosine of 3x minus 4. But analysis, that is the holy grail. That's where the highest tier marks live. That's when you get a complex differential equation involving e to the ax plus b. And you must separate the variables, integrate both sides, solve for the constant using specific boundary conditions, and then critically evaluate the model's validity. That requires a fully connected, conceptual understanding built entirely on causality. You have to know exactly why we divide by the derivative of that inner linear function.
Here is the absolute truth. Top-performing students do not just memorize formulas. They build an adaptable architecture. I call this the mathematics success blueprint. When an exam throws a completely novel, terrifying context your way, say a kinematics question where velocity is given by a really complex inverse function, your brain isn't going to freeze. Why? Because you have mastered the precise definitions and causal relationships. You can transfer your skills to literally any scenario. You understand fundamentally that integration represents accumulation. You know the structural rules for linear inner functions inside out, and because of that, you can confidently execute the mathematical operation regardless of whatever weird outer context the examiner dressed the question up in.
Section 3. The procedural framework, or as I like to call it, the method mark strategy.
Let's talk about how the grading actually works. In Cambridge mathematics, the final answer mark, the A mark, is literally only a fraction of your total score. The vast majority of points are M marks, method marks. Examiners are actively looking for reasons to award you points based on your logical process, even if you accidentally drop a negative sign right at the very end. But here's the catch. That process must be highly visible and completely standardized. We use a 5-step sequence. Step 1, identify the key elements. What is the command word? What is the function type? What are the specific A and B values? Step 2, apply the relevant principles by clearly stating your structural rule. Step 3, execute the analysis through extremely clear line-by-line working. Step 4, verify your results. You do this by quickly differentiating your integrated answer in your head to see if you get back to the original function. Step 5, present the format appropriately. So say you're integrating sine of 2x plus 1. You mentally note it's trigonometric with an inner linear function where a equals 2. You systematically apply the negative cosine rule, you multiply by 1 over 2, you verify by differentiating it backwards, and you boldly add that constant of integration. It transforms absolute chaos into undeniable logic.
Now, presentation is honestly just as vital as the calculation itself if you want to secure those professional skills marks. Proper headings organize your multi-part questions effectively. Correct terminology is absolutely essential. Don't write, "I solved it," state clearly, integrating with respect to x. Appropriate formats mean you must leave your answers in exact form, with surds or in terms of pi, unless significant figures are specifically requested by the command word. Finally, clear annotation of your steps acts as a massive signal to the examiner that you are a highly competent mathematician, allowing them to follow your logic with absolute, unwavering confidence. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to the Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Problem solving and evaluation. Adopting the evaluative mindset. The absolute most successful candidates critically evaluate their own problem-solving steps using a powerful 3-part mantra: deconstruct, solve, evaluate. Imagine a complex data source showing the bounded area under the curve of y equals sec squared of 3x. Before writing a single integral symbol, an evaluative mind scans the limits and the asymptotes, recognizing that as limits approach an asymptote, the area might actually trend toward infinity. Let's do a quick interactive challenge. Imagine a flawed sample of working, where a student tries to integrate 1 over 2x minus 5 between the limits of 1 and 2. They write down,
Natural log of 2x minus 5. They plug in the 2, they plug in the 1, and they calculate the difference. Can you spot the massive flaw there? First, they completely forgot the 1 over r rule, omitting the 1 over 2 multiplier entirely. But worse, plugging in the lower limit of 1 gives a negative inside the logarithm. This highlights exactly why those absolute value signs are mandatory, not optional. Spotting those structural gaps? That is the evaluative mindset in full practice.
Evaluating the quality of your mathematical evidence is what pushes you into those elite, highest-scoring brackets. Step 1, identify the limitations. Does your mathematical model actually hold true for all values of x? Step 2, question your assumptions. Did you accidentally assume a constant rate of change in a scenario where one absolutely doesn't exist? Step 3, consider alternative interpretations. Let's put this into practice by evaluating a classic improper integral. Why integrating e to the negative 2x between 0 and infinity yields a finite area despite the physical region being infinitely long. The core principle here is that the integral of the decaying exponential converges. When you substitute the limits into your integrated function, which is negative 1/2 e to the negative 2x, it reveals that as the upper limit approaches infinity, the exponential term approaches 0. That leaves just the lower limit calculation. Therefore, the total accumulated area evaluates precisely to a finite exact value of 1/2. Understanding that conceptually is massive.
This deep evaluative process is especially crucial when you are analyzing mathematical models. Quite often, an exam will ask you to compare two completely different functional behaviors. A basic comparison, which scores low, only identifies similarities, maybe just vaguely noting that both models show exponential decay. But critical analysis, that identifies similarities and differences using sophisticated comparative connectives. A top answer states, while Model A utilizes an e to the ax+b structure, resulting in rapid decay, Model B, it uses rigorously supported numerical evidence derived from the calculated integrals, and it draws firm, justified conclusions about which exact model is more appropriate for the given real-world scenario. That is how you speed-write a perfect, high-scoring evaluative paragraph. Section 5. Final Examiner Insights. Let's look at the ultimate insider secrets for the 9709 syllabus. I need you to treat this insight with the gravity of a literal legal mandate. Principal examiner reports reveal candidates consistently confuse terminology. Always define your terms before using them in extended responses. When you are explaining your integration steps, you must use precise vocabulary. Say integrand. Say limits of integration. Say constant of integration. Do not vaguely refer to the number at the end. Using professional terminology builds immense credibility with the person grading your paper. Furthermore, you must decode your command words perfectly. If the paper demands an exact value, putting down decimals scores you an instant 0. If it commands you to show that, every single intermediate step of your structural framework must be highly visible. Now, to ensure you never, ever forget this systematic approach under the intense ticking clock pressure of the exam hall, we utilize a structural memory hack. Create a mnemonic for these linear compound integrals. I highly recommend the acronym IRCA. Identify the function, reverse the chain rule, check the derivative, add the constant. Writing IRCA right at the top of your paper the second the exam begins instantly locks in your integration framework. That completely prevents cognitive overload before it even has a chance to start. This ties perfectly into our 3 rules that guarantee top marks: command word decoding, Peel framework application for your evaluative answers, and maintaining a strict time management matrix. So, as you sit down at your desk to tackle your very next past paper, how exactly will you proceed? Are you going to be like Alex or Sam? Will you rely on anxious rote memorization and incredibly rushed calculations, just closing your eyes and hoping the numbers magically fall into place? Or will you cast the right spell? Will you execute the examiner's playbook, applying rigorous structural frameworks, evaluating your logical steps, and systematically securing every single method mark available? The choice is entirely in your hands. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.